All right, so in problem 11.7, we're going to have this setting, and it says that all carrying wires produce electromagnetic radiation, including the electrical wiring running into, through, and out of our homes. High frequency EM radiation is thought to be a cause of cancer. The lower frequencies associated with household current are generally assumed to be harmless. Investigate the relationship between current configuration and type of cancer. Researchers visited the addresses of a random sample of children who had died of some form of cancer, leukemia, lymphoma, or some other type, and classified the wiring configuration outside the dwelling as either a high current configuration or a low current configuration. And here are the data. Okay, so it shows the high current configuration across the rows, the low current configuration across the bottom row, leukemia, first column, lymphoma, and other cancers. That's the three columns. Okay, so computer software was used to analyze the data. The output included the value chi-square equals 0.425. The appropriate degrees of freedom for this chi-square statistic is, okay, so we have a chi-square test of homogeneity. And what you're going to do for this is you're going to, degrees of freedom will be equal to the rows minus 1 times the columns minus 1. Rows minus 1. So then there's 2 rows, so this will just be 1. And there's 3 columns, 1, 2, 3. So it's just 1 times 2. So then the degrees of freedom will be 2. The answer will be B. Expected count of cases with lymphoma in homes with an HCC, so a high current configuration. So if you're looking across the first row, is, so the expected counts. So one way to, well, there's an equation for this where expected counts is equal to multiplying the row total by the column total divided by the overall total. It can be row total times column total and divided by the overall total. So we care about the cases with lymphoma with with a high current configuration. So we care about this value here. But remember, these are the observed values. What would we expect the value to be here if there wasn't a difference, or if there wasn't an association between the type of current and the prevalence of cancer? So let's go ahead and just write down the totals first in the right and bottom rows. So 52 and 84, so 86. For some reason, I don't trust myself when I'm using the calculator. 84 plus 52, the 136 here. Squeeze that in here. 10 plus 21, 31. 17 plus 31, 38, 48. Across the rows, 52, 62, 69, 79. And here we got 84, 21, and 31. Got, 136 again. And then so the overall total, the total will be 79 plus 136. You get 215. Okay, so to find the expected counts for the cases with lymphoma and homes with an HCC, we're gonna look, our row total will be 79. So we're gonna take 79. And the column total for this one will be 31. So we're gonna take 79 multiplied by 31 and divided by 215. And it just has the answer in that form, so the answer is A, you can see. All right, number 9. Which of the following may we conclude based on the test results? Okay, so we got a chi-square test of 0.43, or a chi-square statistic of 0.435. Doesn't specify an alpha level, so when it doesn't, we're gonna go with an alpha level of 0.05, 5%. And since our alpha level, since our alpha level is much smaller than our p-value, or in other words, our p-value is greater than you know our our alpha level, our p-value is actually I didn't even calculate the p-value. What does it mean? Sure, let me calculate the p-value. That was confusing. Okay, so going back to that, let's find a p-value that corresponds with this distribution, chi-square distribution. Um, in other words, we want to find the 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 proportion or the area to the right of this chi-square distribution, where chi squared is 0.435. And our degrees of freedom, we already found to be 2. So like I did in the previous set of problems, you can just use your calculator to run this. So go to distribution, second bars, and then go to chi-square CDF. And remember, it's lower bound. In this case, it's 0.435. Upper bound, just go like a million or something, infinity essentially. Then followed by your degrees of freedom, which is 2. And that'll give us a p-value of 0.8. Geez. Okay, so then since our p-value is much greater than our alpha, we failed to reject HO. Failed to reject HO. So then we're basically saying that we don't have convincing evidence that there's an association between the wiring configuration and the type of cancer. So not gonna be A, not B, not C. There's not yeah, it's gonna be B. The answer would be B. All right, problem 10, a type 1 error would occur if we found convincing evidence that, remember, type 1 is we reject HO when HO is true. It's type 1. Type 2, we failed to reject HO when the alternative is true. For type 1, we reject the null hypothesis when the null hypothesis is true. So again, that's a mistake. So our null hypothesis is that there is no association between the type of wiring and the cancer causes. But since we rejected it, we're saying that we found evidence that there is an association. So basically we found evidence that there is an association. So we basically think that there's an association between the cancer type and the type of wiring, but there actually isn't. So We think there is an association, but there actually isn't. So let's look to see which of these best words have. So HC causes cancer when it actually did. We can't say, first off, we can't also say anything besides dealing with causes just because we didn't do an experiment. It's simply an observational study. So we can't say cause for sure. It won't be A or B. C, there is no association with the type of wiring in the form of cancer. There actually is. So this would be a type 2 error. This would be an example of a type 2. Problem D, there is an association between a type of wiring and the form of cancer when there is actually no association. So we thought there was an association, but there wasn't. So then this is going to be your answer. Is the null hypothesis true in that case? The answer will be B. All right, so there you go. I hope that helps.